Chapter 7, the quantum mechanical model of the atom. Whoops, having problems. Okay, there we go. So the beginning of quantum mechanics. This is probably not the best topic to have on the day after daylight savings time, but it is what it is and we got to deal with it. Okay, so until the beginning of the 20th century, it was believed that all physical phenomena were deterministic. What does that mean? That means that all matter behaves in the same way, follows the same laws, regardless of the size of that matter. Work done at that time, beginning of the 20th century, by a lot of very famous physicists, including Albert Einstein. Work discovered, okay, that's not a great sentence, is it? Physicists discovered that for subatomic particles like electrons, the present condition does not determine the future condition. So what does that mean? Well, if you throw a baseball, you can predict from the beginning of the throw where the baseball will end up. And our brains, through practice, become rather adept at that. We can anticipate where the ball's going to go. If you shoot an electron down a path and measure where it lands and shoot a second electron in exactly the same way, it will probably land in a different place. This does not match up with what we observe with regular objects, things that we can see. So this was very, very strange. So the behavior of the very small, also known as the absolutely small or the quantum world. These are particles that are so small that they do not obey the regular laws of physics. They behave very differently than the large or macroscopic world. Macroscopic means things that we can see with our eyes. Then there's microscopic, which requires a microscope, and these things are smaller than that. You cannot see them with an optical microscope. So these absolutely small particles, like electrons are the only ones we're going to really worry about. When these are unobserved, they can exist in two states simultaneously. And that's something that's really kind of hard to get your mind around. So if we think about an unobserved radioactive nucleus, a radioactive nucleus will emit particles. It is not constantly emitting particles. It does this every once in a while. But it can simultaneously be emitting a particle and not emitting a particle. Is that disturbing? Does that bother you? It bothers me. How can you be doing something and not doing something at the same time? Well, things that are absolutely small don't have to follow the regular rules. Electrons are incredibly small. They fall into this category of absolutely small. If you think about a single speck of dust, you can see it, but it's pretty tiny, right? A single speck of dust has more electrons in it than the number of people who have ever lived on Earth. That's a lot of electrons. All the people who have ever lived on Earth. Lots and lots of electrons. So that gives us, helps us to get some sort of an understanding of how small an electron is. All atoms have electrons in them, and it's the behavior of the electrons that determines a lot of the behavior of the atoms. We cannot directly observe electrons. We can't even directly observe the atoms themselves, and the electrons are much, much smaller. Electrons are so small that by observing the electron, we change its behavior. Just observing it causes its behavior to change. So we can't see them, but we can observe them in sort of indirect ways. Even shining a light on an electron causes it to change its behavior. That's very strange, because that seems to imply that the electron is choosing to do one thing or another. when of course it isn't. It doesn't have a will. It's not alive. But we'll see an example of how shining a light on an electron causes it to behave differently. So I've got some videos to show you today. Have you heard of Schrödinger's cat? There's a lot of funny jokes and stuff about Schrödinger's cat. It was actually a thought experiment. And keep in mind that the purpose of this was to determine that quantum behavior, quantum strangeness, does not translate to the macroscopic world. It doesn't work. So we're going to watch a couple of videos here.
This wouldn't be a YouTube channel without a cat video. So without further ado, we present Schrödinger's cat. I'm sure you've heard some version of this famous thought experiment. You put a cat in a bunker with some unstable gunpowder that has a 50% chance of blowing up in the next minute, and a 50% chance of doing nothing. The gunpowder is Einstein's version. Schrödinger preferred poisonous gas. But whatever. So until we look in the bunker, we don't know whether the cat is dead or alive. And when we do look, it is either dead or alive. So if we repeat the experiment enough times with enough cats and bunkers and gunpowder, we'll see that half the time, Kitty survives, and half the time, Kitty goes bye-bye. The quantum mechanical interpretation is that before we look, the cat is in a superposition. It's both dead and alive. And our act of looking forces nature's decision. So our curiosity kills the cat. But what about the cat's perspective? Well, the cat either sees the gunpowder explode or not. So inside the bunker, we actually have these two possibilities. The powder explodes and the cat sees it explode, or the powder doesn't explode and the cat doesn't see it explode. There's no option, the powder explodes and the cat doesn't see it explode. So the cat's reality becomes entangled with the outcome of the experiment. And it's our observation of the experiment that forces nature to collapse to one option or the other. But we're like the cat too. Either the cat dies and we see it dead, or the cat lives and we see it alive. So who's observing us to force nature to collapse to one reality? Or do both possibilities happen in parallel within a larger multiverse? This collapsing to one reality problem is one of the biggest unanswered questions in quantum physics. So for Kitty's sake, can I have answer, please?
So that's a pretty cool channel called 1 Minute Physics. And if you're curious, I highly encourage you to go check out some of their other videos. Whoops. Come on.
Hello and welcome to I Don't Think That Means What You Think It Means, where we look at bits of scientific theory that have wiggled their way into popular culture and have taken on a life of their own. Today we're talking about Schrödinger's cat, a famous thought experiment devised by the Austrian physicist Erwin Schrödinger, who helped piece physics back together after Einstein and his crew blew a giant frickin' hole in it back in the early 20th century. It's hard to overstate how much of a giant crap circus the 1920s were for physicists. Until then, everything had pretty much just been good old-fashioned Newtonian physics, where you could observe objects moving and predict how they react to various forces. Then along comes all this new research into subatomic particles that shows that they don't act predictably at all. In fact, sometimes stuff seems to be two different things at once, like an electron and a beam might act like a particle sometimes and like a wave at other times. And to make things even more the more you try to observe and measure these particles, the less naturally they behave. My friends, I shall now introduce you to one of the biggest mind flogs of quantum mechanics. It's called superposition. The idea that a particle can exist in all of its theoretically possible states at the same time. So Schrödinger came up with this thought experiment to help everybody understand. Say you have a cat, and you put the cat into a steel chamber for an hour with a vial of deadly gas, a Geiger counter, a hammer, and a tiny bit of something radioactive. Bear with me here. Now say that there's a 50-50 chance that one of the radioatoms is going to decay and release some radiation within that hour. If one of the atoms decays, the Geiger counter is going to trigger the hammer, shattering the vial of poisonous gas. Really, Schrödinger? This is not the best way to get people behind the idea of funding sciences. So there's a 50% chance that at the end of the hour, that vial has been broken and the cat is dead. And an equally good chance that the vial hasn't been broken and the cat's just kicking it $100 for supper. But what's actually happening in the box? According to quantum mechanics, any one of those radioactive atoms would be in a superposition of being both decayed and not decayed at the same time. Because that's how quantum objects act. So then, that decayed atom will have both killed and not killed the cat, right? Well, that's the logical conclusion, but a cat isn't a quantum object. A cat is a big, normal thing that obeys nice, old-fashioned Newtonian laws. So it, just like every other cat in history, is either alive or dead. Schrödinger's point, at least one of them, is that the two objects are subject to two separate sets of laws that can't be reconciled. In order to know whether the atom is decayed or not, and whether the cat is dead or not, you have to open the box and see. But in quantum mechanics, the state of superposition can't be observed. So when the evil mad scientist finally opens the chamber to observe, the superposition collapses and the outcome is ensured. Today, Schrödinger's cat is often talked about as some kind of undead zombie cat, or discussed as if the cat is actually both alive and dead in the box. But Schrödinger's point wasn't to prove that you can make a cat be both alive and dead, but instead to prove that the quantum world doesn't mesh together well with the, like normal world. Alternatively, the point is that the universe is pretty freaking weird. There are other interpretations of quantum mechanics that might resolve the paradox, but none of them are particularly easy to test. My favorite, of course, is the many worlds interpretation that states that at the end of the experiment, and at the end of every superposition, new alternate universes are created. In this case, one in which the cat is alive, and one in which the cat is dead. And to be clear, I don't like this interpretation because I think it's the most likely one. I like it because I think it's such an excellent plot device for science fiction novels. If you have any questions, and I'm sure you do, ask them in the comments below, and I'll, do my best. Also, if you have an idea for I don't think that means what you think it means, please let us know about that too.
Anybody have any questions? Can a cat be both dead and alive at the same time? No, of course it can't. It's not possible. But an electron can behave as a particle and as a wave at the same time until you observe it. And when you observe it, it will become one or the other. So the superposition collapses. It can't be both at the same time if we're looking at it. I don't know about you, but I find this whole topic a bit confusing. It's hard to get your mind around it. So just to make you feel a little better about that, Bohr, who is one of the guys who worked on this, said anyone who is not shocked by quantum mechanics has not understood it. Schrödinger wrote, I don't like it, and I'm sorry I ever had anything to do with it. He was one of the main guys working on this stuff. Albert Einstein, I think everybody's heard of him. He attempted unsuccessfully to disprove quantum mechanics until he died. He didn't like it either. He says God doesn't play dice with the universe. So this is not something that physicists liked, but they were looking for, I guess you could call it truth, but they're investigating the universe, and this is what was fitting with their observations, like it or not. So the quantum mechanical model explains the manner in which electrons exist and how they behave. It helps us to understand and predict the properties of atoms that are directly related to the behavior of the electrons. The behavior of the electrons affects how the atoms behave. And if we want to know how atoms behave, we have to understand, at least on some level, how the electrons behave. Some of the behavior of atoms that are affected by the electrons are why some elements are metals and others are nonmetals. We learned about the periodic table and that most of the elements are metals, and those are on the left side. The nonmetals are on the right side. But why? Why is oxygen not a metal? Why do some elements gain one electron when they form an ion? Others gain two. Fluoride gains one electron. Oxygen gains two electrons. Why? It has to do with the behavior of the electrons. Some elements are very reactive, like hydrogen. Others are fairly practically inert. Helium doesn't seem to do anything. And there are a lot of other periodic properties in the periodic table that we'll be looking at, and electron behavior is what helps us to understand those.